want to find the maximum and minimum value, what do you have to do? How do we find that maximum minimum value now in calculus? Not in grade science. Now, what do we do?
Set the derivative to 0.
Good. We set the derivative to 0 because that's going to tell us where the tangents are horizontal. And wherever the tangents are horizontal, we know that we have a max or a min. So it's always your first derivative equal to 0. So whenever you guys see greatest possible area, minimum surface area, smallest possible surface area, you know that you're optimizing, and that means we need to take the first derivative and set it equal to 0. Now, with these questions, sometimes when you guys read them, you're not sure what to take the derivative of. So let's read this question and let's try to figure it out. So a farmer purchases 750 meters of fencing to build a rectangular pig pen. What dimensions will produce the greatest possible area? We want the area to be maximized. Greatest possible area. That means you're going to be taking the derivative of area. Okay, derivative of area, because that's what you're maximizing. All right, so we need to come up with an area equation. Well, we know area is equal to length times width, right? In this case, I'm just going to use x and y. Doesn't really matter, length, width, x, y. Can I take the derivative here? How would I take the derivative here? I've got two variables. Do you guys know how to take the derivative when you have more than one variable? No, the answer is no. So in order for me to be able to take this derivative, I need to get rid of one of my variables. Which variable do you think I should get rid of here?
X or y.
Yeah, x or y, it doesn't really matter. But I'm going to get rid of the y because that's normally when we take the derivative, we always have x as our independent variable. Okay? All right, so how do I get rid of y? How do I substitute in for y? What other information do we have here?
The perimeter.
Yeah, we have the perimeter, and it's a rectangle. So what's perimeter of a rectangle?
2x plus 2y.
Yeah, thank you. Who's talking to me right now? Is this Steven?
Brian.
Oh, Brian. I'm sorry. Thank you, Brian. Okay, so 2x plus 2y. All right, and then what else do I know?
That's equal to 750.
Thank you, Brian. Okay, so now I have another equation. From here, I can rearrange this equation to solve for y. Right? So I can see that 750 minus 2x equals 2y, and then I just divide by 2 to get y. And so y is equal to 375 minus, yes, dividing everything by 2. Any questions so far? Yes.
Not really talking, but people so much to go on some days, right, I writing working for realizing how to make sense.
Oh, you're on 3.4, not 3.3? Is that what you're saying?
Yes, I was like, had on 3.4 and that doesn't make any sense.
Oh, that's so funny. Okay, so y equals 375 minus x. What should I do now? What's the whole point of doing this? Why did I do this? To sub in for y. So I'm going to take that and I'm going to sub in for y. Now, I only have one variable, so I can take the derivative. So what do you guys think I should do? Should I do a product rule here, or should I expand, simplify, and then take the derivative? What do you guys think? What's better?
Set it equal to 0.
Not yet. Hold on. Listen to the, so here,
Oh, yeah.
yeah, it's okay, it's okay. So here, I need to take the derivative. I have two options. I can use the product rule because I have two functions being multiplied together, or I can just expand this to make my life easier. You guys see that? And now I can take the derivative of this using just the power law. So now I want to take my derivative. So taking the derivative is very simple. It's just 375 minus 2x. And as Brian told us, we're going to set this equal to 0. Because I want to maximize area. I want to find out what value of x is going to give me the greatest possible area. And now I just solve for x. And this is an exact value, so I'm just going to change it to a decimal because we're talking about measurement. It makes sense to do so. If I had a number, in some cases we will also round, right? Because we're talking about measurement. All right, so x equals 187.5. So that's telling me what either my length or my width should be, yes? And now I'm going to solve for y. So once I know x, I sub back into my other equation to get my y. And surprise, surprise, it's the same value. Are you surprised? Why are you not surprised? Yeah, squares are what? Yes, squares are always optimal. He said squares are awful. Squares are always optimal. We know that to get the maximum area of a rectangle, it will always be a square. Good. What about if you want to minimize perimeter? What if you want the smallest perimeter of a rectangle? What shape will you get? Also a square. Okay? So maximum area, square. Minimal perimeter, square. Okay, so now that all we need is a statement. We're done. So therefore, to optimize area, the dimensions should be 187.5 meters by 187.5. Now, we learned that if your domain is restricted, you have to set your endpoint. Is my domain restricted? Can x be anything? Can y be anything? What do you guys think?
No,
No. Why not?
because you only have 750 meters of fencing.
You got it. And do we have a negative x value?
No.
No. I'm talking about length, right? So we can't have a negative x value, and yes, we have a maximum of 750 meters of fencing. So these are our restrictions. So for my restrictions, I know that x has to be greater than 0. But I also know that 2x has to be less than 750. Does everyone understand where I got that from? It's from this equation right here. 750 equals 2x plus 2y. So if I have my smallest y possible, the smallest y possible is 0. So if my y is 0, then that gives me the greatest value that x can be. Right? So that's how I get that value. So 2x is less than 750, which means that x is less than 375. I have just found my endpoints. Okay? So if I just found my endpoint, I'm finding that x has to be greater than 0, but less than 375. Where's my endpoint? And so now we just have to sub them in. Where do I sub them into? I sub them into area. That's what we're trying to maximize. So I'm gonna find A at 0, and I'm gonna see what it equals. And I'm gonna find A at 375, and I'm gonna see what it equals. So go ahead and tell me what we get here. If I sub 0 into A, what do I get? You get 0 and 0. So what we notice now is that my endpoints do not affect my solution. Yes? They're definitely not the maximum. Right? Definitely the values I found for F is the maximum. Okay? The value I found for F. Good. And Y. Oh. Yeah. Yeah.
We just sort of like, I guess this is really the old business, but like, if you just sort of, like, drew what zero represents, it is a very flat object.
I'm sorry, what do you mean?
Like, like in this case, the endpoint represents like, it's like all the length allocated to being small, but no area.
You have to show the process.
Yes.
But yes, I know what you mean. It's kind of obvious, but.
Yes.
Oh no, I keep deleting my notes. Hold on, guys. Let me put it back. Okay, note. Note that boundaries will usually produce results that are not possible or that are unrealistic. Also, oftentimes determining the boundaries can be a challenge. So not so much in cases like this, but once you start getting into volume, where you're going to start having cubic dimensions, then boundaries can be a challenge. So what we say is, with very simple ones like this, where you do have a degree of 1 or a degree of 2, then you can go ahead and find your boundaries. But once you start getting into volume, you don't have to worry about finding the boundaries. And the reason is, they never change, they never affect your maximum. Okay? So there's really no point to go through all that, and in the end it's for nothing. Okay? So on a test, if I give you one like this, yes, you're going to check your boundaries. How do you know? Because it's area and perimeter. But if I give you one that's volume, you don't have to worry about checking the restrictions. Okay? And oftentimes on a test, I will say, don't worry about restrictions on this question, show all restrictions for this question. Okay? Good. Are there any questions? This is pretty simple. No? We're good? You guys have done these types of problems, just not in this way. Right? So you guys have solved these types of problems. Okay, example 2. A carpenter uses an 8-meter squared sheet of plywood to build a square-based open-top box. What dimensions will yield the maximum volume, and what is the maximum volume? What's our idea? First of all, what are we maximizing?
Volume.
Yeah, thank you. We're maximizing volume. So because we're maximizing volume, that's what I'm taking the derivative of. Okay, we're setting the derivative of volume equal to 0. All right, so volume. What would the volume here be? What's the volume of a cube? Or I shouldn't say a cube. We don't know that it's a cube. Of this square-based prism. What's volume?
X squared H.
Good. It's always area of the base times height. Excellent. Area of the base, which is x squared, and then times height. Good. The fact that it's open top doesn't affect the volume, correct? Okay, so I got to take the derivative of this. Can I take the derivative?
No.
No, I have too many variables, right? I've got an x and I have an h. And we haven't learned how to do the derivative of this. Not yet. We will, but not yet. So, we don't know how to take the derivative here, so what do I need to do? Yes. How? You're right. How? So
Surface
what
area.
of information is here? A carpenter uses this much material to build a square base open top box. So they're telling us how much material. What are they giving us? I think somebody said it at home.
Surface area.
Yeah, they're giving you surface area. Now be careful here because it's an open top and that's going to affect the surface area. So how do I find the surface area of this figure? What do I do? You find the area of each side and then you add them all together, right? So the area of my base is x squared. The area of my sides is? What's the area of?
XH.
Yeah, good, x times h. And how many are there? Yeah. So that is your surface area. And we know that the surface area is equal to 8. Okay, what do I do next?
Isolate H.
Yeah, solve for h. So 8 minus x squared and then divided by 4x. All right, get h by itself. Okay, what do I do next? Why did I do this? Is anybody at home there? Are you guys with me?
Sub it into the original equation.
Good. We sub it into volume. And we know that volume was x squared times h. Put it in here. And I need to take the derivative. But before I take the derivative, I'm going to clean this up because I want to make my life easy. So what does this clean up to? No one? So 8x squared divided by 4x, which will then leave me with 2x. And then minus x to the 4 divided by x gives me x cubed and over 4, yes? So 1 over 4. Now I'm ready to take the derivative. 2 minus 3 over 4, x squared, set it equals to 0. And I solve for that. And so I'm left with x squared equals 8 over 3. And now to solve for x, we take the square root. Whenever you take a square root, what do you need to do?
Plus or minus.
Good. Whenever you take a square root, you always have to show the plus or minus. But we know in this case, because we are talking about length, we know that x has to be greater than 0. We only need the positive. So we found that. Now, I need to find it. I found one dimension, I need to find the other. And so just for them, we already know what h is. H is equal to 8 minus x squared divided by 4x. And so we set it. And you can round this to 2 decimal places too. What do we get for H? So 8 minus 8 over 3 divided by 4 times root 8. What do we get? You guys all have calculators. You should be able to find this very quickly. H equals? Oh, guys, you guys are killing me.
0.82.
Good. Okay. Now, we say therefore, the dimensions of the box are, so what's root 8 over 3 as a decimal?
$1.63.
Perfect. And this, that's my base, right? So 1.63 meters by 1.63 meters by 0.82 meters. Those are the dimensions of the box. Have we completely answered this question?
No.
No. What do we need to find? Yeah, we need to find the volume. So we sub in. And the 2 decimal places, please. What is the volume? $2.18 meters. Okay, so you don't normally, like I said to you, with volume and surface area, you're not usually going to have to state restrictions, but I'm going to show you how to do it anyway for this one. So to verify our solution, test endpoints to determine the max or the minimum. So let's find our restriction. Well, one restriction, because it's length, we know x is always going to be greater than 0. So that's nice and easy. To find my other restriction, I have to go to my other formula. Now, where is it? Here. Here. So, if my other dimension is 0, then what will my x equal? That's what you want to find. So if my other dimension is 0, because that's the lowest number that it can be. So here I would have h is equal to 0, and then solve for x. So if h is equal to 0 and I solve for x, I can see that 8 equals x. So that means that x equals root 8. Yeah? That's where the other restriction comes from. That your other variable equals to 0. We know that we only take the positive, right? We don't have to worry about the negative here. So x is less than 8. So overall, my restriction is this. And so now I have to sub in 0 and I have to sub in root 8. Where do I sub it into? What you're maximizing, which is volume. So sub in, tell me what you get. B at 0 is 0, it's very easy to see, that's 4 times 8. And over here, when we sub in, this also comes out to be 0. So again, Did our endpoints affect our solution? They did not. And they very rarely do with these types of problems. Okay? Where they're going to affect your solution is when you're talking about revenue, profit, but not when you're talking about dimensions. Okay? So there will be cases where the boundaries must be tested and they will affect your solution. Surface area, area volume is not one of those situations. Okay? All right, alternative method. So you guys are going to learn this, but I guess I'll show it to you now just as a little preview. An alternative method is to use what we call the first derivative test to verify that our critical point is an optimal value. So what you do is you find what the max and the min are, and we found that value, right? We found the value here to test, the x value. And take a point just to the left of it and to the right of it. And see if you're going from a negative slope to a positive slope. And if you are, then you know that you have a minimum value. If you are going from a positive slope to a negative slope, then you know that you have a maximum value. This is not really necessary here because in the question they tell you find the maximum value. I didn't have to test if it was a maximum, and they told me to find the maximum. And so it came out to be a maximum. Okay? But that's not always going to be the case. And sometimes you have to determine whether it's a max or a min. And if you have to determine whether it's a max or a min, this is a good way to do that. Check the slope to the left, check the slope to the right. If you're going from a negative to a positive, you have a minimum. If you're going from a positive to a negative, then you know you must have a maximum. Right? Okay, we're going to talk more about this, so don't worry too much about this. A cylindrical can must hold 1 liter, which is 1,000 centimeters cubed of oil. Find the dimensions of the can that will minimize the amount of metal required to make the can. What are we taking the derivative of? Yes, you got it. We want to minimize surface area, right? How much metal you're using to make the can. That's surface area. So first derivative of surface area, and then you set it equal to 0. All right, so that means we need the equation for surface area. Surface area, who remembers? We have a cylinder. Who remembers? If I cut this cylinder right here, just cut it right down the middle. What is that round piece that goes around the side, the lateral side of this cylinder? What does it open up to be? So take scissors and just cut this cylinder up. What does it come out to be? What's the neck here? What shapes do you have?
Rectangle.
Good. The middle is a rectangle, and then you have 2 circles for the top and the bottom. Okay, very good. It's a rectangle. What are the dimensions of that rectangle? So if I'm going to cut this, what is the length? We know the width of it will be the height. Yes, we can very clearly see that. So what would the length of it be? Yes. Beautiful. The circumference of the circle, right? It will be the circumference of the circle. If I unroll that, I'm going to see that that rectangle, the dimensions of it is going to be the height and by the circumference of the circle. Good. So that means my surface area is equal to 2 pi r squared plus 2 pi rh. Why? What does the first half of my expression here represent? What's the 2 pi rh? What is that? What is that representing? Yes. No, careful.
Okay, that's not the thing.
Yeah.
Yes.
Excellent. Very good. So the 2 pi r squared represents our circle. Pi r squared is the area of a circle. So 2 pi r squared is my circle. Yes? No, it's okay. And then I'm wearing a mask too. 2 pi rh is now the dimensions of the rectangle. 2 pi r is your circumference, h is your height. Okay, so that's length times width right here. Good. Little way to remember the formula, right? Now I need to take the derivative. Can I take the derivative? Can I take the derivative here?
No.
No, I have too many variables. I have too many variables. So, I need another formula. They give me another piece of information. What do they tell me? Yeah, they tell us what the volume must be. They tell us that the volume of this can has to be 1 liter. So what is the volume of this cylinder? Remember, guys, it's always area of the base times height for any shape that has symmetry. So what I mean by that, if you're talking about a rectangular prism, a triangular prism, any type of prism, you have the same base at the bottom and the top. So your volume is always going to be area of the base times height. If you have something like a pyramid or a cone, now all of a sudden you have to divide by 3. It's still going to be area of the base times height, but now you need to divide by 3 because it's going into a point. Right? Good. Okay, so the volume, area of the base times height. Well, my base is a circle. It's pi r squared. And we know that it must equal 1,000 centimeters cubed. And now I'm going to solve for it. Now that I know H, I sum it back into my first equation. And I take the derivative. And now we're going to clean this up before we go ahead. Oops, sorry. Look what I just did. Oh. We're finding the derivative of surface area. There you go. Now clean it up and then find your derivative. So I'm left with 2,000 and r to the exponent -1. I set it up like this because I know I'm taking my derivative, right? And so because I'm taking the derivative, I want those variables up. I don't want to have to do a quotient rule here, right? Okay, so now taking the derivative, what is the derivative of 2 pi r squared? Not all of you at once. What's going on? Guys, why are you guys not talking to me today? I know it's a snowy day and you want to stay in bed, but get out of bed and help me.
4 pi r.
4 pi r, and then keep going.
Minus 2,000 r to the -2.
Thank you. This is still Brian, right?
No, this is Nicholas.
Oh, for goodness sake. Nicholas. Thank you, Nicholas. Okay, so 4 pi r minus 2,000 r to the -2. We set it equal to 0. And yes, you must show this step setting it equal to 0. And now you can change it back to a denominator if you want, if it helps you solve, no big deal. So you can change this back. Because I think that usually helps you guys solve. It's up to you. And we're solving for r, so I need to divide. And what do you get? So 2,000 divided by 4 will be, this is painful. Okay, 500. And then I'm dividing by the pi r, right? Or you can, if it's easier for you guys, you can do it this way. Pi r cubed. Yes? And then you're dividing by your pi. and then you're taking your cube root. And of course, with the cube root, there is no need to take a plus or minus, right? You can have a negative in a cube root. Okay, and so R is approximately equal to 5.42. Now that I know R, I have to find H. And we know that H equals, I can't see it, 1,000 divided by pi. Squared. Oops. And tell me what that's approximately equal to. And I know you guys already know this, but remember for pi, you're using the pi button in your calculator. You are not using 3.14. Okay, you're using the pi button in your calculator. So what do we get here? .84. Therefore, the can should have a radius of 5.42 centimeters and a height of 10.84. Now, if you had to find the restrictions here, this is where it starts to get challenging. So, obviously we know radius has to be greater than 0, so that's not a big deal. But then, when we're looking at our second equation here for surface area, what you have to do, or sorry, for volume, I apologize, where is it? There? You have to set your H equal to 0 and solve it. Okay? So, setting your H equal to 0 and solving will produce 1,000 is less than pi r squared. Right? And then you have to take the square root. So it starts getting messy. Okay, so that's why we don't bother, because when you go ahead and do it, it's not going to affect it anyway. Good. Are there any questions here? No questions? We're all good? All right.
Yup.
Thank you. So to verify a solution, test endpoints if necessary, or you can use the first derivative test to find your critical point, or you can use what's called a second derivative test to determine if critical points are a maximum or minimum by examining concavity. So these are all concepts that we're going to learn eventually, so you don't need to learn them now. But I just want you guys to know that there are many, many ways to determine whether a value is a max or not. Okay, and these are them. So there's the first derivative test, which, as I said to you before, once you find those max or min values, we call them critical points. Then you just test the left and the right and see if you're going from a minus to a positive or a positive to a negative. Or you can use what's called a second derivative test. You have to find the second derivative. Okay? And what this does is it gives us what are called inflection points. And these inflection points tell us where a curve is changing from concave up to concave down, which helps us also determine. Okay? Well, just a little preview, not necessary. Okay? So continuing from example 3, so if I wanted to use that second derivative test, I find the second derivative, which is 4 pi plus 4,000 r to the negative 3. That's just by taking another derivative, right? Second derivative. From here, now, I check. When I sub in my r, is it positive or is it negative? And if it is positive, then we know that it's concave up. Well, if it's concave up, then we know it has to be a minimum. If you sub in and you get a negative value, well, if it's a negative value, then you know it has to be concave down, and so therefore it has to be a maximum. Okay, so yet another way to find max and min. Okay? Cool. So notice I subbed in our answer, what we got, and I got a positive result, so it is in fact a minimum. Now, we already knew it was a minimum because the question told us, yeah? So that's why this is not necessary yet. Just a little preview. Cool? All right, so your homework for this section. Okay, so now we're going to move to 3.4. Example 1. Find the dimensions of a 355 milliliter cylindrical soft drink can that will minimize production costs if the metal used on the top of the can costs $2 per centimeter squared, and the metal used to construct the rest of the can costs $1.20 per centimeter squared. What am I taking the derivative of? Yeah. Good, cost. And how am I finding my cost here? You're absolutely right. We want to minimize cost.
Of surface area.
Yeah. We want to minimize cost. And we're talking about the cost of making the can, which is coming from surface area. So we now need to combine surface area together with how much it costs for each material. Okay? So let's come up with a cost equation. So first of all, I have a bottom and I have a top. Yes? They're circles. So area of a circle is?
Pi r squared.
Good, and I've got two of them. So it's 2 pi r squared. That is the surface area. But it costs what? Oh, sorry, just the top. So look at here. We know that we have 2 pi r squared. Absolutely, yes. But do they both cost the same amount to build both?
No.
No. The metal used on top is $2.
There's just pi r squared.
Yeah, and then times $2. So it's still 2 pi r squared, but it's because of the value, not because there's two circles.
Right.
Yep. Now, I have to construct the rest of the can. Well, I have another circle to deal with. The other circle is pi r squared, but it only costs $1.20. And now I have the lateral side, which we've already learned is 2 pi RH, but it also has to be multiplied by 1.2. And now let's simplify this. multiplying 1.2 times 2, we know it's 2.2. Okay, this is now what I need to take the derivative of. Can I take the derivative of this?
No,
No, why not? You're right.
too
Why
many
not?
variables.
Too many variables. So, what else does it tell us? There's another.
Volume?
Yeah, they're telling us the volume. They didn't say volume, but we know it's the volume because it says that the can hold 350 milliliters. That's the volume. Okay, so what's the volume of a cylinder? We've already seen it. Volume of a cylinder. Area of the base. Times height. We know that it equals 355. And now we solve for H. Now, we have our two equations. We sub 2 into 1. To get rid of that variable. So C is equal to. So here, guys, what I want you to notice is I have two like terms, don't I? Bring them together. Simplify this and then take your derivative. So 2.4 times 355 is 852. The pi's will cancel, and one of my r's will cancel. But we want to bring it up because we're going to take the derivative of it. Taking my derivative, I have 3.2 times 2. By r minus 852 r to the exponent negative 2. Set that equal to 0 and solve. And now divide by 6.4 and take your 6.4 pi and take your 2. So when decimal place, what is r? So what's r?
About 3.49.
Okay, good. And here's 3.5. And I will tell you guys how to round on a test, whether I want 2 decimal places, whether I want 1, I will let you know. And now we sub it in. And what do we get for each?
About 9.22.
9.32, is that what you said? Is it
9.22.
9.22. And you're using the pi button in your calculator, right? You're not using 3.14.
Yep, the pi button.
Perfect. Okay, good. So therefore, to minimize cost, the radius should be 9.2 centimeters, and the height,
I miss you mixed it up.
oh, I apologize. Thank you, I just realized. Should be 3.5 centimeters, and the height should be 9.2. Cool?
Yes. On the test, do you want us to sub in the fraction or the decimal?
You know what, it's okay to put in the decimal, it's all right, I know, because in order to get an exact value, right, technically you should be subbing in 852 divided by 6.4 pi to group, but it's okay. You can go ahead and just round it. The
Okay.
reason, yeah, the reason is, realistically in life, when you're building something, at some point you're gonna have to round, right? Like if you're cutting a piece of wood, you're cutting a piece of tin, at the end of the day, you need to round, yes? And so it's okay to round. So to minimize cost, yeah, thank you. To minimize cost, the radius should be 3.5 centimeters, right there, I think we're done. Do I need to do restrictions here? No. Okay, I told you guys for volume, we don't need to worry about restrictions. Okay, so we're not gonna do restrictions.
So miss restrictions only for area.
You got it.
Okay. Thanks.
And on the test, I will be very specific, okay? So I will say, include all restrictions, or not include restrictions. I'll be very clear. Okay, example 2. The Greater Toronto Circus Company plans a yearly acrobatic show. Last year, tickets sold for $80 and 1,000 people attended. A survey shows that for every $4 increase in price, attendance will decrease by 25, excuse me. So 25 less people will come every time you increase the price by $4. So if you increase the price by $8, 50 less people will come. Okay, and so on and so forth. If the theater's capacity is 1,200 and ticket prices cannot exceed $140, so they don't want the ticket price to go over $140. What ticket price will maximize revenue, and what is the maximum revenue? Okay, first of all, what's revenue? We're talking about revenue. What is revenue?
The amount of money you make,
Yeah, okay, so
not the cost.
you go ahead. Okay, so how much money the company takes in? That's what revenue is. How much money the company takes in. However, then there are costs. You got to pay out your costs. Once you pay your overhead, you pay your staff, you pay whatever, then what's left is your profit. The revenue is how much money comes in. So if you're talking just about revenue, then revenue should be however much the ticket costs, the ticket price, times however many people attend. That's how much money is being collected. True? Yeah, true. So for revenue, I know it's equal to the cost of the ticket, or the price of the ticket, times the number of tickets. Well, we've got a situation here, yes? We don't know what the ticket price is. We're trying to find out what the ticket price should be. So I'm going to introduce a variable x, and I'm going to say let x represent. And what am I going to let x represent? I want you guys to go back. We've all done this in grade 10, grade 11.
Number of $4 increases.
Yes, excellent. X is going to represent how many times we increase the price by $4. Perfect. Okay. We know that if I increase the price by $4, less people are gonna attend. 25 less people will attend. So the cost right now of the ticket is $80. But we're gonna add some increment of $4. We don't know how many times we're gonna add $4, so it's $4 times the number of times we increase it. Well, my number of tickets right now is 1,000. 1,000 people is what came last year. Last
Is
year,
it just minus 25x?
yeah. Good. So 25 people for every time the price is increased. So 25 times that. If I increase that price, so if I increase by $8, increase it 2 times, 50 less people will attend, right? If I increase it 3 times, $12, then 75 less people will attend, and so on and so forth. This is what I'm trying to maximize. So because this is what I'm trying to maximize, this is what I need to find the derivative of. Now, do I have any extra variables here? No, so I don't have to worry about another equation. I'm good. I've got 2 variables, an independent and a dependent. I can go ahead and take the derivative. Now it's up to you. You can do a product rule, or you can expand and simplify. It's totally up to you. I'm going to expand and simplify to give me 80,000 and then minus 2,000x plus 4,000x minus 100x squared. Cleaning up your middle terms. And now you can take your derivative. Again, you could have done a product rule. It will work. It's still a derivative, right? Instead of having to expand it. Okay, so now when I take the derivative, it's very simple. It's simply 2,000 minus 200. Nice and simple. We set it equal to 0, and we solve it. And don't forget to show this step. And so x is equal to 10. That means we have to increase this ticket price to what? What would the ticket price be? Would it be $90? What's the ticket price?
120.
Yeah, good. You're increasing it 10 times by $4. You're increasing it by $40. Am I done? So that's it. The ticket price is just $120 and we're done. What do you guys think?
Endpoints.
Yeah, you got to test your boundaries here because we know that only a certain amount of people fit in here and the price cannot exceed 140. Well, I think we can already see that the price is not going to exceed 140, but we want to make sure that that capacity is also not over, right? So let's check our boundaries. Okay, so our boundaries are the number of people that can be in there. We know it has to be less than 1,200. Less than or equal to, right? 1,200 is in there. The cost has to be less than or equal to $140. Which equation represents the number of people that attend? Is it the 80 plus 4x or the 1,000 minus 25x? Which one represents the people attending? Yes. Good. And so that's your expression there, and now you can solve for x. The other equation represents the price, the ticket price. So that's our cost. And again, just solve for x. Okay, So I have negative 25x is less than or equal to 200. I now divide both sides by negative 25. Who remembers what happens when you divide an inequality?
You
by-
flip it, right?
Yep, you gotta flip it. Now I ended up with a negative number. X is greater than or equal to negative 8. Well, if X represents the number of price increases, what does negative 8 represent? Yes. Good. Instead of increasing the price, you're decreasing the price, right? You're getting a negative X. X represents the number of increases. So if you get a negative, that means you're actually decreasing the price. Okay. Over here now, we solve. So my overall restrictions here is this. So X has to be between negative 8 and 15. Our answer did fall between negative 8 and 15, which is good. It's 10, so that's good. And now we got to check those boundaries and make sure that they don't produce a higher revenue. Okay? So, the revenue when you decrease the price 8 times. The revenue when you increase the price 10 times. And the revenue when you increase the price 15 times. Tell me what you get for each one.
So for R -8,
Yeah.
you get 57,600.
Thank you, Nicholas. You have more?
I'm inputting it right now.
Yeah, no worries.
For R of 10, you get 90,000.
Good. So far, this is better. And then 15, whenever somebody has it.
87,500.
So what gives us the most money?
10.
Yeah. So the boundaries didn't affect our answer, but you have to check, because sometimes they will. Therefore, to maximize revenue, the price should be $120. Have we answered the question fully? What else? No.
Maximum revenue.
Yeah, good. So, should be $120 for a maximum revenue of $90,000.
Miss, I have
Yeah.
a question. How'd you get 10 again? For yeah, because like you have -8, 15, and you have 10 too, which gives you 90K.
So,
It's just yeah.
find your first derivative, okay, so finding your first derivative equal to 0, this gave me the local max.
Oh yeah, okay, I got it.
Yeah, which in this case also happens to be your absolute max.
Yeah, I just forgot what was the value of the local max. Okay, got it.
It's okay. So first derivative equals to 0. And then I check my increment. That's how I got $3. And sometimes you might get more than one maximum value, right? From your critical points, you have to test more than one. And you guys already saw that. You saw that in 3.2. Are there any questions?
Miss,
Yeah.
how do we know that when should we verify the results?
So whenever the only ones that you should not verify the results is volume. Everything else, you should be checking your restrictions. Volume is the only one that I don't want you to worry about because it gets a little, it gets a little complicated. But everything else, you should be checking your restrictions.
Oh, okay.
The reason is, these are not just graphs, right, that go on forever and ever and ever. They have restrictions. So there's a start point and there's an end point because there are restrictions. And so just like in 3.2, you must check those boundaries. You have to check those endpoints. And this is the homework now for this section. 151, numbers 1, 4 to 7, 9, 10, 11, 8, 12 to 15. Note, number 12, there's a typo. It should be $20 per centimeter squared and $30 per centimeter squared. Note regarding revenue problem. If you solve and get a decimal answer, for example, x equals 2.5, check to ensure that the number of people are whole numbers. So for example, you can't have 100.7 people. So in order to maximize, if you need 100.7 people, well, that means you actually need 101 people. So you're going to be a little bit over, but you're going to have to round that to the nearest whole number, right? Now, depending on the question, guys, sometimes you have to round down and sometimes you have to round up, whatever makes sense. Yes.
Yeah, there's also, it is fine, for example, in the example 2 just now, where it says, where we represent $4 increase, I mean, that's all that fine.
It's money, because it's just money, right? So if you're dealing with example 2 where it's revenue, but you're not talking about the number of people, you're talking about money, right? And your money is a decimal, that's fine, right? Because you can break it up into smaller parts. You can't break people up into smaller parts, right? Okay, good. And this is your review homework, guys, that you can start working on if you wish. Well, you should. You should start working on it. So let me look at my schedule because I want to see what I have. Yeah, so tomorrow, guys, I've given you guys a review period. I've actually included a review period. So it's up to you. Would you guys rather have the review period, or would you rather that I just start with chapter 4, and then that will give you an extra review day before your CPT? What do you guys think is better? Double review day there, or would you rather you need the time right now to catch up and you need the review homework day tomorrow? Yes, I'll pull up the time. So I'm going to show you. Okay, so here's our schedule. So what you're going to notice is, let me just put it here. All right, I've included one review day now before your chapter 4 test. Tomorrow is a full review day. There's no lesson tomorrow, okay? Full review. I've also have another review day before your chapter 4 test. Okay, so before your chapter 4 test, I've included a review day, one full day, let's say. And then at the end, when you guys write your CPT, you have one review day. So we've got 3 days there, just for review. What I'm saying is, if you guys would rather have 2 review days before